Marieb Hoehn Anatomy and Physiology, 10th edition, Chapter 24, Nutrition, Metabolism, and Energy Balance. Are you a food lover? We are too. In fact, most people fall into one of two camps, those who live to eat and those who eat to live. The saying, "you are what you eat," is true in that part of the food we eat is converted to our living flesh. In other words, our bodies use some nutrients to build cell structures, replace worn-out parts, and synthesize functional molecules. However, most nutrients we ingest are used as metabolic fuel. That is, they are oxidized and transformed to ATP, the chemical energy form used by the cells. In Chapter 23, we talked about how foods are digested and absorbed, but what happens to these foods once they enter the blood? We will answer this question as we examine both the nature of nutrients and their metabolic roles. Part 1. Nutrients. A nutrient is a substance in food the body uses to promote normal growth, maintenance, and repair. The nutrients needed for health divide into 5 categories. 3 of these, carbohydrates, lipids, and proteins, are macronutrients that make up the bulk of what we eat. The 4th and 5th categories, vitamins and minerals, though equally crucial for health, are micronutrients required in only minute amounts. Water, which accounts for about 60% by volume of the food we eat, is considered by some to also be a nutrient. We described its importance in the body in Chapter 2, so here we consider only the 5 nutrient categories listed above. At least 45 and possibly 50 molecules called essential nutrients cannot be made fast enough to meet the body's needs, so our diet must provide them. As long as we ingest all the essential nutrients, the body can synthesize the hundreds of additional molecules required for life and good health. The ability of cells, especially liver cells, to convert one type of molecule to another is truly remarkable. These interconversions allow the body to use a wide range of foods and to adjust to varying food intakes, while essential is a standard way to describe the chemicals that must be obtained from outside sources. Both essential and non-essential nutrients are equally vital for normal functioning. Most foods offer a combination of nutrients. A balanced diet of foods from each of the different food groups normally guarantees adequate amounts of all the needed nutrients and adequate energy. The energy value of foods is measured in kilocalories or kcal. 1 kilocalorie is the amount of heat energy needed to raise the temperature of 1 kilogram of water to 1 degree Celsius or 1.8 degrees Fahrenheit. This unit is the calorie that dieters count so conscientiously. Various organizations release dietary recommendations. Most of these emphasize eating more vegetables, whole grains, and fruits. For example, the U.S. Department of Agriculture, or USDA guidelines, are represented as portions of a dinner plate. The image suggests how consumers might plan their meals relative to amounts and variety of foods from each food group. The MyPlate website provides details on healthy choices in each food group, as well as personalized information according to age, sex, and activity level. Nutrition advice is constantly in flux and often mired in the self-interest of food companies. Nonetheless, basic dietary principles have not changed in years and are not in dispute. Eat only what you need, eat plenty of fruits, vegetables, and whole grains, avoid junk food. Carbohydrates, lipids, and proteins supply energy and are used as building blocks. Carbohydrates, dietary sources. Except for milk sugar, lactose, and negligible amounts of glycogen in meats, all the carbohydrates we ingest are derived from plants. Sugars, monosaccharides and disaccharides, come from fruits, sugarcane, sugar beets, honey, and milk. The polysaccharide starch is found in grains and vegetables. 2 varieties of polysaccharides provide fiber. Cellulose, plentiful in most vegetables, is not digested by humans but provides roughage or insoluble fiber, which increases the bulk of the stool and facilitates defecation. Soluble fiber, such as pectin found in apples and citrus fruits, reduces blood cholesterol levels. Uses in the body. The monosaccharide glucose is the carbohydrate molecule ultimately used as fuel by body cells to produce ATP. Carbohydrate digestion also yields fructose and galactose, but the liver converts these monosaccharides to glucose before they enter the general circulation. Many body cells also use fats as energy sources, but neurons and red blood cells rely almost entirely on glucose for their energy needs. Because even a temporary shortage of blood glucose can severely depress brain function and lead to neuron death, the body carefully monitors and regulates blood glucose levels. Any glucose in excess of what is needed for ATP synthesis is converted to glycogen or fat and stored for later use. Other uses of monosaccharides are meager. Small amounts of pentose sugars are used to synthesize nucleic acids, and a variety of sugars are attached to externally facing plasma membrane proteins and lipids. Dietary requirements. The low-carbohydrate diet of the Inuit, Eskimos, and the high-carbohydrate diet of peoples in the Far East indicate that humans can be healthy even with wide variations in carbohydrate intake. The recommended intake to maintain health is 45 to 65% of total calorie intake, with the emphasis on complex carbohydrates, whole grains and vegetables, rather than simple carbohydrates, monosaccharides and disaccharides. American adults typically consume about 46% of dietary food energy in the form of carbohydrates. Because starchy foods, rice, pasta, and breads, cost less than meat and other high-protein foods, carbohydrates make up an even greater percentage of the diet in low-income groups. Highly processed carbohydrate foods, such as candy and soft drinks, only provide concentrated energy sources, so-called empty calories. Eating refined, sugary foods instead of more complex carbohydrates may cause nutritional deficiencies as well as obesity. Table 24.1 lists other possible consequences of excessive intake of carbohydrates. Lipids, dietary sources. The most abundant dietary lipids are triglycerides. We eat saturated fats in animal products such as meat and dairy foods, in a few tropical plant products such as coconut, and in hydrogenated oils, trans fats, such as margarine and solid shortenings used in baking. Unsaturated fats are present in seeds, nuts, olive oil, and most vegetable oils. Major sources of cholesterol are egg yolk, meats and organ meats, shellfish, and milk products. However, the liver produces about 85% of blood cholesterol, regardless of dietary intake. The liver is also adept at converting one fatty acid to another, but it cannot synthesize linoleic acid, a fatty acid component of lecithin. For this reason, linoleic acid, an omega-6 fatty acid, is an essential fatty acid that must be ingested. Linolenic acid, an omega-3 fatty acid, is also essential. Fortunately, most vegetable oils contain both linoleic and linolenic acids. Uses in the body. Fats have fallen into disfavor, particularly among those for whom the battle of the bulge is constant. But fats make foods tender, flaky, or creamy, and make us feel full and satisfied. Fats in the body are necessary for several reasons. Fatty deposits in adipose tissue provide 1. A protective cushion around body organs, 2. An insulating layer beneath the skin, and 3. An easy-to-store concentrated source of energy. Phospholipids are an integral component of myelin sheaths and cellular membranes. Cholesterol is a stabilizing component of plasma membranes and is the precursor from which bile salts, steroid hormones, and other essential molecules are formed. Unlike triglycerides, cholesterol is not used for energy. Prostaglandins, regulatory molecules formed from linoleic acid via arachidonic acid, play a role in smooth muscle contraction, control of blood pressure, and inflammation. Triglycerides are the major energy fuel of skeletal muscle and hepatocytes, and fats help the body absorb fat-soluble vitamins. Daily requirements. Fats represent over 40% of the calories in the typical American diet. There are no precise recommendations on amount or type of dietary fats, but the American Heart Association suggests fat should represent 30% or less of total caloric intake. Saturated fat should be limited to 10% or less of total fat intake, and daily cholesterol intake should be no more than 300 milligrams, the amount in 1.5 egg yolks. The goal of these recommendations is to keep total blood cholesterol below 200 milligrams per deciliter. Because a diet high in saturated fats and cholesterol may contribute to cardiovascular disease, these are wise guidelines. Table 24.1 summarizes sources of the various lipid classes and consequences of deficiency or excessive intake. Proteins. Dietary sources. Animal products contain the highest quality proteins. In other words, those with the greatest amount and best ratios of essential amino acids. Proteins in eggs, milk, fish, and most meats are complete proteins that meet all the body's amino acid requirements for tissue maintenance and growth. Legumes, beans and peas, nuts, and cereals are protein-rich, but their proteins are nutritionally incomplete because they are low in one or more of the essential amino acids. The exception to this generalization is soybeans, which provide plant-derived complete proteins. Strict vegetarians must carefully plan their diets to obtain all the essential amino acids and prevent protein malnutrition. When ingested together, cereal grains and legumes provide all the essential amino acids. Some combination of these foods is found in the diets of all cultures, for instance, the rice and beans seen on nearly every plate in a Mexican restaurant. For non-vegetarians, grains and legumes are useful as partial substitutes for more expensive animal proteins. Uses in the body. Proteins are important structural materials of the body, including, for example, keratin in skin, collagen and elastin in connective tissues, and muscle proteins. In addition, functional proteins such as enzymes and some hormones regulate an incredible variety of body functions. Whether amino acids are used to synthesize new proteins or burned for energy depends on a number of factors. The all or none rule. All amino acids needed to make a particular protein must be present in a cell at the same time and in sufficient amounts. If one is missing, the protein cannot be made. Because essential amino acids cannot be stored, those not used immediately to build proteins are oxidized for energy or converted to carbohydrates or fats. Adequacy of caloric intake. For optimal protein synthesis, the diet must supply sufficient carbohydrate or fat calories for ATP production. When it doesn't, dietary and tissue proteins are used for energy. Hormonal controls. Certain hormones called anabolic hormones accelerate protein synthesis and growth. The effects of these hormones vary continually throughout life. For example, pituitary growth hormone stimulates tissue growth during childhood and conserves protein in adults, and the sex hormones trigger the growth spurt of adolescence. Other hormones, such as the adrenal glucocorticoids released during stress, enhance protein breakdown and conversion of amino acids to glucose. In healthy adults, the rate of protein synthesis equals the rate of protein breakdown and loss, a homeostatic state called nitrogen balance. The body is in nitrogen balance when the amount of nitrogen ingested in proteins equals the amount excreted in urine and feces. The body is in positive nitrogen balance when the amount of protein incorporated into tissue is greater than the amount being broken down and used for energy, the normal situation in growing children and pregnant women. A positive balance also occurs when tissues are being repaired following illness or injury. In negative nitrogen balance, protein breakdown for energy exceeds the amount of protein being incorporated into the tissues. This occurs during physical and emotional stress, for example, infection, injury, or burns, when the quality or quantity of dietary protein is poor, or during starvation. Dietary requirements. Besides supplying essential amino acids, dietary proteins furnish the raw materials for making non-essential amino acids and various non-protein nitrogen-containing substances. The amount of protein a person needs to ingest reflects his or her age, size, metabolic rate, and the need to build new proteins, whether the body is in positive nitrogen balance. As a rule of thumb, nutritionists recommend a daily intake of 0.8 grams per kilogram of body weight. Most vitamins act as coenzymes. Minerals have many roles in the body. Vitamins. Vitamins, vita translating to life, are organic compounds needed in minute amounts for growth and good health. Unlike other organic nutrients, vitamins do not serve as an energy source, nor as building blocks, but they are crucial in helping the body use those nutrients that do. Without vitamins, all the carbohydrates, proteins, and fats we eat would be useless. Most vitamins function as coenzymes or parts of coenzymes, which act with an enzyme to accomplish a particular chemical task. For example, the B vitamins act as coenzymes when glucose is oxidized for energy. Most vitamins are not made in the body, so we must ingest them in foods or vitamin supplements. The exceptions are vitamin D made in the skin and small amounts of B vitamins and vitamin K synthesized by intestinal bacteria. In addition, the body can convert beta-carotene, the orange pigment in carrots and other foods, to vitamin A. For this reason, beta-carotene and substances like it are called provitamins. Vitamins are found in all major food groups, but no one food contains all the required vitamins. A balanced diet is the best way to ensure a full vitamin complement. Initially, vitamins were given letter designations that indicated the order of their discovery. Although more chemically descriptive names have been assigned to them, this earlier terminology is still commonly used. Vitamins are either water-soluble or fat-soluble. Water-soluble vitamins, the B-complex vitamins and vitamin C, are absorbed along with water from the gastrointestinal tract. The exception is vitamin B12. To be absorbed, it must bind to intrinsic factor, a stomach secretion. The body's lean tissue stores insignificant amounts of water-soluble vitamins, and any ingested amounts not taken up by cells within an hour or so are excreted in urine. Consequently, health problems resulting from excessive levels of these vitamins are rare. Fat-soluble vitamins, A, D, E, and K, or ADEC, bind to ingested lipids and are absorbed along with their digestion products. Anything that interferes with fat absorption also interferes with the uptake of fat-soluble vitamins. Except for vitamin K, fat-soluble vitamins are stored in the body, and pathologies due to fat-soluble vitamin toxicity, particularly excess vitamin A, are well documented. Metabolism uses oxygen, and during these reactions, some potentially harmful free radicals are generated. Vitamins C, E, and A, in the form of its dimmer beta-carotene, and the mineral selenium participate in antioxidant reactions that neutralize tissue-damaging free radicals. The whole story of how antioxidants interact in the body is still murky, but chemists propose that, much like a bucket brigade, they pass the dangerous free electron from one molecule to the next until a chemical, such as glutathione, finally absorbs it and the body flushes it out in urine. Broccoli, cabbage, cauliflower, and Brussels sprouts are all good sources of vitamins A and C. The notion that megadoses of vitamin supplements are the road to eternal youth and glowing health is useless at best, and at worst may cause serious health problems, particularly in the case of fat-soluble vitamins. Table 24.2 contains an overview of the roles of vitamins in the body. Minerals. The body requires moderate amounts of 7 minerals: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium, and trace amounts of about a dozen others. Minerals make up about 4% of the body by weight, with calcium and phosphorus, as bone salts, accounting for about 3/4 of this amount. Minerals, like vitamins, are not used for fuel, but work with other nutrients to ensure a smoothly functioning body. Incorporating minerals into structures makes them stronger. For example, calcium, phosphorus, and magnesium salts hardens the teeth and strengthen the skeleton. Most minerals are ionized in body fluids or bound to organic compounds to form phospholipids, hormones, and various proteins. For example, iron is essential to the oxygen-binding heme of hemoglobin, and sodium and chloride ions are the major electrolytes in the blood. The amount of a particular mineral in the body gives very few clues to its importance in body function. For example, just a few milligrams of iodine required for thyroid hormone synthesis can make a critical difference to health. A fine balance between uptake and excretion is crucial for retaining needed amounts of minerals while preventing toxic overload. Sodium, present in virtually all natural and minimally processed foods, poses little or no health risk. However, the large amounts added to processed foods and sprinkled on prior to eating may contribute to fluid retention and high blood pressure. Fats and sugars are practically devoid of minerals, and highly refined cereals and grains are poor sources. The most mineral-rich foods are vegetables, legumes, milk, and some meats.